In this section, we're going to look at work. Work is basically a process of transfer of energy. This is a process of transfer of energy. Okay. Doing work involves applying a force while displacing an object. So it depends on the force applied on an object and the displacement over which the force is applied. Okay, so force depends, or work depends on the force applied on the object that is, the greater the force, the greater the amount of work done. And also it depends on the displacement over which the force is applied. The displacement over which the force is applied. The greater the displacement over which the force is applied, the greater the amount of work done. Now we're going to look at a special case, and then we're going to generalize later. So work done by constant force, work done by a constant force while displacing the object in a straight line. While displacing the object in a straight line. We're going to look at this special case first, and then we're going to generalize. Okay, suppose we have this object over here, okay, and let's say it's being displaced in this straight line displacement. It displaced from here to here. Let's say this distance over here is d, and let's say the force applied is this force F over here. Okay, so the work done in taking this object from here to here depends on two factors. Of course, it depends on the force, but it's only the component of force in the direction of the displacement that contributes to the work. This component over here does not contribute to the work done. So it's only the component of force in the direction of the displacement that contributes to the work done. So the greater this force is, the greater the amount of work. And also the greater the distance over which this force is applied, the greater the amount of work done. Okay, so we can say, if we use W for work, okay, so we can say the work is proportional to F parallel, is also proportional to the distance. Actually, the constant proportionality is defined to be 1, so you get the following formula for work. It is the component of the force in the direction of the displacement times the distance. So in this special case, work is simply the product of the component of the force in the direction of the displacement and the distance over which the force is applied, this distance over here. Okay, now if this angle is theta, of course, F parallel equals the magnitude of the force times cosine of theta, right? So with that, we have this form for the work done. That is F distance times cosine of theta. Okay, so this is the formula for work for the case where the force is constant and the displacement is a straight line. Okay, so in this formula, F is magnitude of force, magnitude of force. In this case, d is a distance, or you can say magnitude of displacement, magnitude of displacement or distance in this case. And then theta is angle between force and displacement. This is angle between force and displacement. Okay, so first let's look at the unit of work. unit of work, as you can see from this formula, is the unit of force, which is Newton, times the unit of distance, which is meter. This one is defined to be the joule and abbreviated by capital J. Okay. Now, work is scalar. It's not a vector. Work is a scalar. It doesn't have directional properties. Okay. And it can be positive, negative, or zero depending on the angle theta. So let's look at the formula. You've got, this is magnitude of force times distance times the cosine of the angle. Okay. Now the magnitude force is always positive. The magnitude, the distance is always positive, but this one could be positive or negative depending on the angle. So for acute angles, this is positive, so the work done will be positive. For obtuse angles, cosine is negative, so the work will be negative, and if theta is 90 degrees, it will be 0, of course. Okay, so work could be positive, negative, or 0 depending on the value of the angle. All right, so let's look at some examples. Suppose I have this object over here, okay, and then displace it to this location over here. Let's say this distance is 10 meters. Let's say I have this is 10 newtons, okay, and let's say this angle is 60 degrees over here. So in this case, the magnitude of force is 10, the distance is 10, theta is the angle between the displacement. You see, this is our displacement. So the angle between the horizontal and this force is 60 degrees, so theta is 60 degrees, and then the work equals F d cosine of theta. So you've got work equals 10 times 10 times cosine of 60. Cosine of 60 is half, so you get 50 joules. Okay. How about if we have like this? Let's say the force is like this, and the object is displaced this way. Okay. So in this case, you see the displacement is this way, and the force is perpendicular to it. So theta is 90 degrees, and cosine of 90 degrees is 0. So this implies the work would be 0. So if the force is perpendicular to the displacement, the work done would be 0, because this force does not contribute anything to the displacement in this direction. Okay. And if you have something like this, let's say this object is displaced at this location over here. Let's say once again this distance is 10, but the force is going this way. Okay, let's say this angle is 60 over here. Now look, theta is the angle between the displacement and the force, right? So this is a displacement over here this way. So the angle we need is this angle over here, the angle between the force and the displacement. So this is 60 degrees. This would be 180 minus 60 degrees, which is 120 degrees. Okay, so the work would be the force, let's say again is 10 newtons times 10 times cosine of 120 degrees. Cosine of 120 degrees is negative half, so it will be negative 50 joules. Now you might ask, how can this move in this direction while the force is in this direction? That can happen if the object is already moving, just like the force of friction does. Okay, its effect would be to slow down the motion. All right, so as you can see over here, if the effect of the force is to hold the motion or to increase the motion, work is positive. But if the effect of the force is to slow down the motion, that is if the angle is obtuse, then work done is negative. So these are the three different cases. If it's acute, it will be positive. If it's 90 degrees, it will be 0. If it is 120 degrees, if it is obtuse angle, work done will be negative. In other words, if the force helps the motion, it is positive. If the work opposes the motion, it's negative. And it's perpendicular to the displacement, it is 0. Okay, so this is the case for the case where the force is constant and the displacement is in a straight line direction. Okay, now we're going to look at the general definition. Okay, that is the force can change from point to point. The path also could be curved. That is, the force could change from point to point. The force can change from point to point, and the path could be curved too, and the path can be curved too. Okay, that's the most general definition. So let's say we have this curve over here like this, and the force maybe changes wildly from point to point. Let's say it's variable everywhere in magnitude, direction, so on. So how do you deal with this case? Okay, so we take a small section over it. Okay, let's call this dr over here, the small displacement. We can assume the force to be constant over this small displacement dr. Okay, let's call this dr, that's infinitesimally small displacement, and we can assume the force over this range to be a constant. Okay, so let's say the force over here is F. So as we've seen before, the work done just on this path, let's call dW, is going to be the force times the displacement times the cosine of the angle between this small displacement, this force. Okay, but if you remember, this is the definition for dot product. You remember this formula? A dot B equals AB cosine of theta. Okay, so this is the dot product in the force and the small displacement dr. Okay, so we have the following: dW equals the force dotted with dr. Okay, and then to find the total work, we just add up the small parts. We do this for all small parts of dr over here, and then we add them up, which means integration. Okay, so the total work done will be the integral of dW, which means the integral of this expression over here. And what are the limits of integration? Well, let's say this is our coordinates over here. This is going to be our initial position vector Ri over here, and this one is going to be our final position vector Rf. So this integral goes from this point, whose position vector is Ri, to this point, whose position vector is Rf. Okay, so the most general definition of work is the following: work equals the integral of the dot product of the force at the point whose position vector is r, and then the small displacement will be dr, and this integral is taken from the initial position vector ri to the final position rf. So this is the most general definition of work. So if the force varies from point to point, if the path is curved and so on, if you just take a small part over here, you do the work on that section and then just add up, which is integration. Okay, now we're going to simplify this for the case where the force is a constant. Now remember, the path is not a straight line, only the force is a constant. All right, so let's look at the case where the force is a constant, the case where the force is a constant. Okay, so in this case we have the general definition: dW equals the integral from the initial position vector to the final position vector of f dot dr. Okay, but if the force is a constant, you can take it out of the integral. This is just a sum of different parts, so you can take the common out, right? So you've got, oh, this is actually the work, I'm sorry, this is the work. So you've got the work equals the force dotted with this integral, dr going from Ri to Rf. Okay, but what does it equal to? This is simply Rf minus Ri. Okay, so the work equals F dotted with final position vector minus initial position vector. Okay, and with this one, this is simply the displacement vector. Okay, it's the displacement vector. So the force is a constant. You've got work equals force dotted with delta r. Okay, graphically, remember, displacement is the vector whose tail is the initial vector and whose head is the final vector. Okay, for example, let's say we have something like this, okay. Now let's say this is my coordinate system over here, so this will be my Ri. Okay, let's say this is a path over which the work is done, and this is my Rf. Okay, so in this formula, delta R is simply this line over here. It doesn't, irrespective of the path followed, this is delta R. Delta R is simply the vector joining the initial position vector to the final position vector. This is our delta R. Okay, so it doesn't matter what the path is, the displacement vector delta R is simply the vector whose tail is the tip of the initial vector, and it is the final vector. Okay, all right. Now let's write this in terms of components. Let's write formula in terms of components. In terms of components, remember f can be written as the x component in the I direction plus the y component in the j direction, and delta R can be written as delta x in the I direction plus delta y in the j direction. Okay, so f delta R times dot with delta R is fx delta x plus fy delta y. Okay, so in terms of components, we can say work equals fx delta x plus fy delta y. This is provided f is a constant. Okay, provided f is a constant. All right, now let's consider an example. Suppose we have a constant force acting on this object. Let's say is being displaced from, this is a quarter of a circle from here to here, let's say. Okay, let's say this is our coordinates over here. Let's say the object is being, this is the path of a circular path. This looks like shorter than this one, but I meant to make it a circle. Okay, this is a circular path. So let's say we take it from here. Let me draw this again. I'm sorry. Suppose we have, let's say this is a circular path, a circle over here. Okay, and this is the coordinate system over here like this. Okay, suppose let's say an object is displaced from here to here on this circular path, and this is, let's say the radius is maybe 0.5 meters. Okay, and the object is being displaced along this path under the influence of the following constant force. Let's say it's maybe 2I plus 3J newtons. Okay, this is a constant force, and the object is being displaced from here to here. Okay, so the question is calculate the work done. We have a constant force, we have this path over here. Okay, so since the force is a constant, the work done is F dot delta R. Okay, since F is constant. Okay, so we have the force, we just have to find delta R. Delta R is this one over here. This is our delta R. Okay, delta R is simply the straight line joining the 2 points irrespective of the path followed. But what is that? This is the initial position vector, this is the final position vector. So our delta R is final position vector minus initial position vector. Okay, now my initial position vector is 0.5 in the negative I direction, right? This vector is 0.5 in the negative I direction. So we've got Ri equals negative 0.5 in the I direction, and Rf, you see this vector over here is my final position vector, and that is 0.5, the radius in the j direction. Okay, so RF is 0.5 in the j direction. Okay, so my displacement, which is RF minus RI, is 0.5 in the j minus negative 0.5 in the I. Okay, so that is 0.5 in the j plus 0.5 in the I. That's my displacement. Okay, and so the work done in this case is F dot delta R. Okay, we have already stated the force over here is 2I plus 3J. This is 2I plus 3J dotted with the displacement 0.5 in the J plus 0.5 in the I. Okay, so that's 2 times 0.5 plus 3 times 0.5. Okay, that is 1 plus 1.5, that is 2.5 joules. Okay, so this is the amount of work done in displacing this object along the circular paths under the influence of this force. So you don't have to follow the paths. The displacement is just the straight line connecting the 2 points. Right. Now, of course, we can write also using the alternate definition of a dot product. You remember A dot B is also defined to be A times B times cosine of theta. Okay, so work, which is F dot delta R, can also be written as the force times the magnitude of the displacement times the cosine of the angle between the displacement and the force. Okay, this is the delta R. We're using this as the magnitude of delta R over here like this. Okay, this is the distance between the initial point and the final point, the straight line distance between the initial point and the final point. Okay, all right. Now let's look once again at the general definition. So we've got work equals the integral from initial position vector to final position vector F dot dr. Okay, now we can write force as the force as x component in the I direction plus Fy in the j direction, and dr can be written as dx in the I direction plus dy in the j direction. So you've got this dr over here, and then these are the components dx and dy. Okay, and then follows that the dot product between f and dr is fx dx plus fy dy. So in terms of components, we can write the following formula for work. This is the integral of for the position, maybe we can use xi yi. Okay, this is the initial position vector, and then for this one you can use xf yf over here, and then you've got the following fx dx plus fy dy. Okay, so this is the formula of work in terms of components. Okay, now let's consider examples of variable forces. Examples with variable forces. Okay, first let's look at one-dimensional force. The force acting on an object varies as a function of x according to the formula. Let's say this is our f vector over here. let's say maybe it is 2x squared in the I direction. Okay, now calculate the work done. Calculate the work done by this force in displacing an object, let's say from x equals 2 meters to x equals 4 meters. Okay, all right, so this is a displacement along the x-axis. This one over here is displaced from x equals 2 to x equals 4. Okay, so it's a displacement in this direction. So our dr is simply dx in this case. If you take small displacement over here, so our dr is simply dx in the I in this case. Okay, and then we have f equals 2x squared in the I direction, and then f dot dr is simply 2x squared times dx. Okay, so the work done, which is f dot dr, is the integral of 2x squared dx, and this goes from x equals 2 to x equals 4. Okay, so we have this is 2x cubed over 3 going from x equals 2 to x equals 3. Okay, so this equals 2 times 3 cubed over 3 minus 2 cubed over 3. Okay, so that's 27 over 3. That's 2 times 27 over 3 minus 8 over 3, and that is 2 times 19, that is 38 over 3 joules. So this would be the work done by this force if the force varies with x according to this formula. Okay, now let's look at a two-dimensional problem. That is where the force depends on both x and y. Okay, the force acting on an object varies with x and y, let's say according to the formula. Let's say this is a force, maybe it is x times y in the I direction, maybe let's say x squared, maybe y cubed in the j direction. This is a force. Okay, now the object is displaced from the origin to the point, let's say 2, 4, to the point 2, 4. All right, so that's what we have. So it's displaced along this line over here. So this is origin, and this is a point 2, 4 over here. Let's say along the straight line joining them, along the straight line joining them. Okay, so the question is calculate the work done. Calculate the work done. Okay, so it's displayed like this. All right. So the force, we have to find F dot dr. Okay, so and so we have to find dr. Okay, so we have to find arbitrary dr over here, which is dx in the I plus dy in the j. Okay, let's say this is dr over here. So dr equals dx in the I plus dy in the j. Okay, so F dot dr is this one. You've got xy in the I direction plus x squared y in the j direction dotted with dx in the I direction plus dy in the j direction would be this is xy dx plus this is a cube over here, cube x squared y cubed times dy. Okay, now we can find the relationship between y and x using this path over here. Okay, so you can say that y over x equals 4 over 2. You see this relationship over here? We can say y over x equals 4 over 2, which means y equals 2x. Basically finding the equation of the line joining 0, 0 and 2, 2. Okay, so the slope is 4 minus 0 over 2 minus 0, which is 2, and the y-intercept is 0. Okay, so we have this relationship over here. So equation of the paths you see the force is applying at these points. So at these points y and x are related by this equation over here. Okay, so this is the equation of the paths. From that also we can obtain an equation between the dy and dx. So taking the differential, we can say dy equals 2 times dx. If you can say dy by dx equals 2, will give you the same thing. Okay, now we can replace y by 2x, and we can replace dy by 2dx. Okay, so with that we have the following expression for f dot dr. F dot dr would be, this is x times y, okay, but y is 2x, right? So this is x times 2x, and then times dx, of course, times dx. And then second term, we have x squared y cubed. We have x squared y cubed, but y is 2x, right? So you've got and dy, you see this one over here is 2dx. Okay, so we can also replace this by 2dx. So we've been able to express this expression just in terms of x. So you've got, this is 2x squared dx plus you've got 8x to the 5 times 2 dx. Okay, so you can factor out dx. So you've got 2x squared plus 16x to the 5 dx. That's it. Okay, and the work done is the integral of f dot dr. Okay, now we just have x. Well, you can say it's a general from Ri to R final. So this is 2x squared plus 16x to the 5 dx. Now we have only x, so the origin, the value of x is 0. And then we're moving to the point 2, 4, which means the value of x is 2 over here. Okay, so this goes from x equals 0 to x equals 2. All right, and then of course we get 2x cubed over 3 plus this is 5 over here, so 16x6 over 6, going from x equals 0 to x equals 2. Okay, so this equals 2 times 2 cubed divided by 3 plus 16 times 2 to the 6 divided by 6. And that's it. So that's 8 times 2. That's 16 over 3. And this one, 2 times 6 is 64. So this is 16 times 64 divided by 6. Or let's say this is 8 and this is 3. So you've got 16 plus 8 times 64 this is for 80 plus 32, maybe 512. 512 plus 16 is 528. Okay, so this will be the amount of work done.